Hello, everybody. Today is Friday, November 20th, and I'm recording this little message or recording this little lecture for you because I am going to be on a small, little, tiny vacation with my family, and we wanted to make sure we didn't lose kind of another day, because we've had a few holidays and things like that. So what we're going to be doing today, so you found the assignment where this video is contained, and what you're going to do is watch this video, and then after this video, you're going to fill in some answers into the text box kind of below. So I'm setting up the assignment to where you're going to enter in some text. And so at the end of this, I'm going to ask you kind of a few questions and basically, yeah, basically that will be your day for today. Rather than kind of our normal kind of process where we will kind of work together on something. Okay, so today we're going to talk about a couple of things the one part of it's going to be something that you can compute, and the other part is going to be something conceptual that I think is important enough to spend time on. It's kind of tough because it's something that we're not going to necessarily be able to, give you a bunch of homework questions on or things like that. But I think it's something that if you understand, if I can find a way to explain it well, if you can understand it, then you will be a long way towards really understanding what we're doing when we're doing a confidence interval estimate. So just to kind of remind everybody, kind of what we've been doing, we've been making what we call confidence interval estimates. So confidence interval estimate. Okay, and the idea behind the confidence interval estimate is basically we start off and we fix a confidence level. Okay. Okay. And then after we fix the confidence level, and like I said, some examples of confidence levels are like a 90% confidence, a 95% confidence, and a 99% confidence. And once we fix that confidence level, we build an interval estimate. Okay, so this is our kind of our second step after we've done that, is we build an interval estimate. Okay, and the way that we build it is we build it by saying that the true value, and this is what we mean by an estimate, is going to be between basically two numbers. And the first number is basically going to be, or the upper end of this interval is going to be some sample percentage, so a sample percentage that we collect, plus this little wiggle room that we call the margin of error. And we set the lower value to be that same sample that we collect minus a margin of error. And the idea is that margin of error, okay, we're basically computing it to be the smallest that it possibly can be, and still reach the confidence level that we set for ourselves in the beginning. And we do so by using this formula. So Z alpha over 2, and we called this, once again, we called this a critical value. Okay, and we multiply this by this thing we call the standard error for this estimate. And if you guys remember, this is kind of in a way the standard deviation of our sample percentages. But once again, we call this the standard error. Okay? And this critical value, if you remember, we choose it depending on the confidence level. Okay, so basically, if we wanted to be 90% confident, we chose 1.645. If we wanted to be 95% confident, we choose 1.960. And if we wanted to be 99% confident, we choose 2.576. And once again, these are those critical values. And the idea is that once again, we're choosing those to reach certain levels of confidence. If we need it to be 99% confidence, we have to choose a larger critical value. If we want to choose if we're willing to live with only 90% confidence in the result, basically we choose a smaller critical value. Okay. So the first question that we're really going to come up with is, so we've done this formula, we've done a few examples with it. We've also done sample size formulas and stuff like that. So we've learned how to kind of manage the margin of error and keep the same confidence. But the big question is what does confidence level actually mean? What do we mean when we say that when I write down that we are 90% confident in the final result? And so that's basically the question that we're going to answer today. Is we're going to come to a definition of confidence level. And then after we come to a definition of confidence level, what I'm going to do is I'm going to be showing you how these critical values are computed, and then show you guys how to adapt it to other confidence levels. Because while 95% is by and large the overwhelmingly most common critical confidence level, there are occasions when our confidence levels, when we have to adjust them to being something other than 90, 95, and 99%, even though those are definitely the most common possible. I mean, the most common values that are used in political polling, opinion polling, and scientific papers and things like that. Okay, so big thing we're asking though is what the hell do we mean by 90% confident or 95% confident? And in order to explain this, I want to go back to an example, and I keep coming back to this example just because it's like our big example of sampling. Okay, and basically understanding confidence level and really understanding a lot of what we're doing with statistical inference really comes down to understanding what we're doing when we are kind of sampling. Okay, and so if you remember the example that we had here, what we did is we basically kind of cheated a little bit, and we said that we had this population. Okay, generally populations are so large that we don't know everything about them, but we used our student, so this is a student survey, basically as a population to sample from. Okay, and in this sample, what we were really looking, or in this population, what we were really looking at was the percentage of students who love stats. And what we found was that in this case, our P, okay, the percentage of students who love stats in our population, and what we had was that it's around 0.29 or 29%. Okay, and what we did is we took a bunch of different samples from this larger population, and we did a bunch of random samples, and I tried to show you guys kind of the process. So what we have up here were samples that were 100 students each, okay, each time. Here they were samples of 50, and here we only had 20 each time we did a sample, and here we only had 5 each time that we did a sample. And if you remember, we kind of talked about kind of how the patterns changed as our sample size got bigger. Okay, and what we're going to focus on today, or what I'm going to do today, is I'm going to focus kind of on 2 particular samples just to kind of get us started. And then what I want us to think about is, what does it actually mean to have a certain confidence in the correctness of your result? Okay, so the first sample, so like I said, we're basically going to do kind of what I would call a tale of 2 samples. And the first sample that we are going to look at, okay, is going to be, I believe it is right, I think I remember it was right here. I forget exactly where it was, but this was our sample 77th, our 77th sample that we had. And what it was we had our 50 people in that sample, And what we ended up getting for the percentage of that sample was around 44% of our students loving stats. Okay, so right up here, I'm just going to go ahead and write this for kind of our first sample. So sample kind of 1, and this is what we're going to pay attention to. Now, the first thing I want you to notice here is that sample 44 is 44% is actually much larger than our P, right? Than the actual proportion of the population that we're pulling from. So, think of it this way, like, we know students only like stats, only about a quarter of the students love stats, but this particular group has a much larger percentage of people loving stats in it. Okay? And what I'm going to do is I am going to create basically a 95% confidence interval, okay, interval estimate. Okay? And basically, once again, when we did this before, we had our n equals to 50, we had our p hat equals to 0.44, and we went through our margin of error formula. Okay, so when I take that margin of error, we have a critical value. Okay, our critical value multiplied by the standard error. Okay, and what we get, and I don't want you to get too focused on the computation, but if you remember, we had our 1.960 if we're using 95% confidence, and then what we would have here is 0.44, 0.56, and this would be over 50. Okay, and so when I do this computation, okay, and like I said, it's not so much about focusing on completing the computation, but what I end up getting is a margin of error of about 13.8 percentage points, or about 0.138. And what this means is that our margin of error, when I combine it with that sample that I got, it's going to be 0.44 plus the 0.138, and once again, the 0.44 minus the 0.138, and what we get is that the P, or at least according to this one according to this one sample, the percentage of students who love stats in the population that I pulled the sample from should be between about 579 and at the low end about 302. Okay? All right. So this is the prediction that we would make, once again, if we had this particular sample sitting in front of us. If we did a survey of 50 students at random, and it turned out that 44% of students love stats, this is the kind of estimate that we would make for the percentage of students who love stats in that population. But one thing I hope you notice is, and like I said, in general, like when we're doing this in practice, we do not know whether we're right or wrong. But in this particular case, I want you to recognize that this 302, okay, this 302 and this 579, that the 0.29 is not inside this interval, okay? And so I'm going to draw like a little sad face here, okay? This is a little sad face here. And the reason it's a little sad face is that I made this interval, I did all this work with the margin of error, and I still ultimately was incorrect. Okay? And what do I mean by being incorrect? Well, basically, I didn't get the right value in this interval. I didn't capture the right value. And the main reason why I didn't catch the right value is that, well, guess what? The actual error, the actual distance from the 44 to that 29, which is like how far things actually are from each other, is equal to, where did I actually have it written down? It's equal to 15 percentage points. And if you notice, the 15 percentage points that we have in actual error is larger than the 13.8 percentage points that I built in to as my wiggle room, right? So my 13.8% kind of stops here, and it doesn't actually capture the true value because that one sample's like too far away. And so we ultimately are incorrect. And this is actually an important thing to understand when we're looking at like a single result, like a single poll or a single uh, a single scientific study. Um, Even with a 95% confidence, right? It sounds like I'm being very confident that the result is correct. But there still is a chance that obviously if I happen to get one of these values, which, once again, there's not that many of them, okay? But if I get one of these values that's too far away, and like I said, I don't know if I got it or not. I don't know if the value that I got was really far away in practical practice. But this 0.44 is too far away, and ultimately it led me to make an incorrect estimate, okay? And to kind of contrast with that, the second sample that I'm going to take is actually going to be a little bit closer. And the second sample that I'm going to focus on was also, once again, a sample of size 50 from this kind of the same group. And it has a sample percentage of about 0.26. So 26%, that's a little under what the true value is. It's about 3 percentage point from the true value. And I'm going to do the exact same thing I did before. Okay, so let's suppose that I had my sample 2 here, which had my n equals to 50, and our p hat equals to 0.26. This value is definitely closer to the real value, though in practice we wouldn't really know that. And I'm going to do the same thing. I'm going to compute a 95% confidence interval estimate. Okay, and once again, the way I do this is by going back to my margin of error formula, using that 1.960, using that critical value, and then computing the standard error, which is 0.26 multiplied by 0.26 times. Wait, hold on one second. I think I did this wrong on my paper, so I'm gonna kind of do it again right here. I'm just sorry. Every once in a while I kind of do the wrong computation on my piece of paper. So what I'm going to have is 0.74. So this will be 0.74, and this will be all over 50. Okay. And when I actually go to do this computation, and like I said, I had it written on a piece of paper, and I made a mistake. But oh, and look, I was almost going to be dumb here and do 1.969 rather than 1.960. I'm off to a ripping good start right here. But anyway, 1.960 times, I'm going to go ahead and let me take the square root there. And this is 0.26 times 0.74, okay? And then we're going to divide that by our 50. Okay, so I got that right there. And what I'm going to get for my margin of error, it's funny, I actually still ended up with the right number. I just wrote down a number wrong. We get a margin of error of about 122, or about 12.2 percentage points. And when we actually use that in a confidence interval, right, we take that 0.26 and add the 122. We take the 0.26 and we subtract the 0.122. And what we're going to get when we actually put those two things together is we get an upper estimate of 0.382 and a 0.138. So we had these two particular values. Now, what I want to point out here is that I'm a lot happier with this estimate. This estimate, if you look at it, I'm doing it in green because basically I'm happy, okay? I'm happy in this case because I know ultimately I'm correct. And once again, I want to remind you guys, in human practice, we don't know if we're correct or wrong. But what I'm showing you is that, this process of doing a confidence interval, okay, sometimes yields a correct answer, In this case, it did, namely because the actual error of about 3 percentage points was actually far smaller than the margin of error that we use to give ourselves our wiggle room. Okay. And, once again, because our margin of error that we built into the estimate was about 12 percentage points, we were only 3 percentage points away from the real value. And so guess what? We nailed it. We got that real value. And once again, because it was kind of close. Okay. And so sometimes we're correct and sometimes we're wrong. Okay. And so with that being stated, okay, what I want to do is I'm going to just drop down the kind of the definition of what we mean when we say a 95% confidence. And because what it really has to do with is this understanding that we are taking it when we get a sample in our hand, that really this is just one sample out of the many possible thousands and thousands and thousands of possible samples that I could have gotten from this population. Even just looking at samples of size 50. These are just 2 little snapshots. And it happened to be in one case I got it right, in another case I got it wrong. Okay, and this is really what confidence level is kind of enumerating for us. Okay, and so what I'm going to drop right below here is basically a definition for confidence level. Okay, it's not really a definition, it's more of an explanation of what we mean when we say that we want to be 95% confident. Okay, and so what I'm going to do is I'm going to go ahead and go to a web browser. Okay, and oh, I actually had this pulled up earlier. I'm sorry. I had to restart my computer to get my mic working, and I forgot to leave this. And so really, I'm just pulling this from a website. Okay, so there's a lot of different websites that have decent definitions. I kind of like this one. And what I'm going to do is I'm going to copy this right here. And we're going to read it. And I'm going to talk about kind of what it really signifies. Okay? And so what this really signifies is, it says the confidence level refers to the percentage of all possible samples that can be expected to include the true population parameter. Okay? Now, what does that mean? Well, in this case here, because that percentage was close to the true value, when I built in my margin of error, the true value was inside that particular interval. And so this is what they mean when they say that it contained the true population parameter. This got 29% inside of it. I was ultimately correct. Now this one here was far enough away from the mean, or far enough away from the true value that it did not contain the true population percentage. True population parameter. And so what the confidence level is really referring to is when we do these samples many, 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 many times, what percentage of those samples are going to yield ultimately correct confidence intervals? Or what of the possible samples are going to be expected to include the true population parameter? Like how many of these, after I build in my margin of error, are going to basically be correct, and how many of them are going to be false? So what our confidence level really is trying to do is trying to make it so that a certain percentage of them are expected to be correct. And the example is, and this uses the 95% confidence, a 95% confidence level implies that 95% of the confidence intervals are going to contain the true population parameter. Or in other words, 95% of these samples are going to be kind of within the margin of error that I compute for each sample. Okay, so 95% are going to actually end up being correct down in this little group here, and about 5% of them are ultimately going to be wrong or too far away, so far away from the true value that even when I build in that wiggle room, that margin of error, I still end up incorrect. Okay? Now, I want you to see this in action. So what I did is I translated these samples that we got here into basically a spreadsheet. And part of the reason that I had to do this is because CODAP sadly does not have some of the functionality that I need to demonstrate this. So I had to go to a spreadsheet, and it's not the perfect interface, and I hope you guys can get something out of this, even though it's not the best way of showing it. Okay, so what I have here are all of these samples that we got there, and what we have here, if you notice, are 200 of them. Okay, and what I did is I put them in order. Okay, I put them from smallest to largest. Okay, then next to it over here, what I did was actually compute how far away the sample was from that true population parameter, that 29%. So when I get a sample of students that only 12% of them love stats, well, guess what? I'm 17% below the true value. 17% below the true value. That's really far away. Okay, now as these numbers go up, I want you to notice how the actual distance, the actual error that I have actually seems to get smaller, namely when I have numbers that are closer to 29. Now 28 right here is only 1 percentage point away. That's definitely really close. And then what happens is then my numbers start getting bigger, okay, and over here notice how there's 1% larger. And then here, these are all 3 percentage points larger, and then 5%, 7%. And then we get all the way over here to a 46 percent students loving stats, and that's 17 percentage points above the real value. Okay, and so I have them nice and color coded right here. So green, basically a really dark green, means that the estimate is really too low. And a white means it's really close when it's really light. Okay, and then the red really stands in for the value is just really, really far away but high. Okay, so that's the actual error. Okay, and then what I did is over here I can adjust the confidence level. And right now I have it set to 95%. And what I've built in is basically the confidence level or the confidence interval that would be computed, okay, with that 95% confidence level. Okay, so if I had a 95% confidence level, the margin of error would be 9 percentage points for this estimate. And we would have an estimate that would take us from 3% at the low end all the way up to 21% at the high end. Now, if you notice here, the true value, that 29%, is not inside this interval. And that's what this particular column kind of represents. So if you notice over here, I have a bunch of no's. And basically, these are all examples where the actual error that I have, the actual distance that these points are away from the true value, is bigger than the margins of error that I was using as my wiggle room, that I computed using this confidence level. Okay, and each of these ended up not containing the true value. It wasn't until we get to this 20% right here that all of a sudden that the distance there, it's close enough to, it's only 9 percentage points away, that once I start building in that margin of error of 11.1%, now I get an interval that's wide enough to actually contain the true value. And so I want you to notice here, I get a bunch of no's for these ones that are extremely small, okay? And then I'm going to get a bunch of yeses all in the middle, okay? And it is until I get to the extremely large ones down here that I once again end up with an interval that is ultimately not containing the true value, largely because the actual error is larger than the margin of error that I was using for my wiggle room here. Okay, and we have a bunch of them that are yeses and a bunch of and just those ones on the edges are no's. Now, what did we just read? We said that if this is a 95% confidence interval estimate, that if we have a 95% confidence, then what we should see is roughly 95% of these samples will actually contain the true value. So I should see about 95% of these things with yeses Okay, and these are 95% of the values that are kind of on the inside here that are closer. They should be yeses, and only about 5% should be nos, should end up failing to contain the real value, basically being wrong. And if you notice here, I have it computed, the percentage of those yeses, and guess what? At a 95% confidence, using this critical value of 1.960, okay, I am going to get about 94.5% of them correct. And this is pretty dang close to what that expected value is. So we said we should be around 95% of the time, of the samples. 95% of these samples end up having the true value in between. And only 5% of them ultimately don't. And what are the 5% that don't? The ones that are far enough away that even after I build in that margin of error, it still fails. It still isn't close enough. Okay? It's still ultimately wrong. Okay? Now, what I want to do is the reason I built it into this particular spreadsheet is not just to show you the 95% confidence, but I also want to show you how changing this value changes the number of yeses that we have. So we already had a 99% as being one of the possible confidence levels. So I'm going to go ahead and set this to 99%. And I want you to watch what happens to some of those no's. Okay, so now, bunk, notice how some of the no's now became yeses. Okay, and even down here, yeah, actually now even these really extreme ones are within the margin of error. Okay, and so I want you to notice, look what happened to the percentage of yeses. Ultimately, the percentage of yeses jumped up to around 98%. Now, it's not a perfect 99%. Part of that is because we only did 200 samples. I think if I did a lot more, we'd probably get closer to the real value. And this isn't like a perfectly normal sample. But if you notice, this value is actually pretty dang close to what we would expect to see. So about 98% of all of my samples ended up producing correct intervals or correct estimates. Okay, and in order to do so, I needed this larger critical value. Notice how it computed the larger critical value right there, 2.576. Now, I will say, though, that this is not for free. Okay, we don't just get to be correct more often. We are being more correct largely because we made our margins of error a lot bigger. Okay, we're basically making our estimate wider. Okay, and remember, wider basically means less specific, less like generally useful. But by making it less generally useful, by building in a lot more wiggle room, by hedging a little bit more, I actually had a higher chance of being correct, and I'm correct more often. Okay. And so that's what we're seeing right here is that even though we have an average margin of error of about 16.4%, which is a lot, which is really big, well, the good side of having that margin of error that large is that, well, guess what? By hedging that much, I am going to be right like almost 99% of the time. Now, let's look at one of the other ones that was like smaller. Like a 90% confidence. So remembering that average margin of error there was about 16.4%. Now I want you to see what happens when I make a 90. Okay. Well, first off, a lot of those yeses or some of those yeses became nos again, and the average margin of error shrank. And once again, we have a smaller critical value. And what's happening here is that you're building smaller amounts of margin of error. You're building smaller wiggle rooms with this procedure using this particular confidence level. You have a smaller margins of error. So you have actually more specific and, in some sense, more precise estimates. Okay. But guess what? Those precise estimates, those estimates that seem really good, are actually wrong a lot more of the times. Namely because now, since we're building in smaller margins of error, ultimately, it doesn't take a value to be that far away in order to so that the actual error ends up exceeding how much we built into the interval. Okay, so if you notice right here, when I had a 90%, the percentage that were ultimately correct dropped all the way down to 92%. Now that's actually a little bit better than we would expect, whereas the one before were a little bit worse. Once again, part of this is because we have such a small sample size here, and it's not like a perfectly, from what I noticed, it's not like a perfectly shaped one. Okay, now another thing that's going to be nice about this is I can also make a confidence level that isn't just one of those three. So what I'm going to do here is I'm going to go ahead and make like a ridiculously low confidence level, like a 0.4. Okay. Now I want you to notice here, 0.4. Well, if you notice here, my margins of error are small AF. Okay, we have like only like 3% margin of error. If you look at my estimates here, they're very narrow. They're very precise, especially for a 50, for a 50 sample size sample. These are very small margins of error. And our critical value is also really tiny. It's less than 1. Okay? And in building that in, I want you to notice now we have like very few successes here. And once again, it's because ultimately I'm not building in a lot of error into each of my computations because of the nature of that formula. I'm only building in just enough error to get successes for the values that are actually already just really, really close. So I'm still succeeding when the thing is 3 percentage points away. But once I get a little bit beyond 3 percentage points, I start failing. So these were 5 percentage points away, and my margin of error was just not enough to compensate for being that far away. And so I ultimately only have 40, in this case, 42% of them ultimately being correct. And, you know, the same thing's going to happen when we go down to like a 20%. Now look how small that critical value is, and look how small our margins of error are. So these are like really, really specific, and these would feel like really, really good estimates because you are being like, you're really narrowing it down. But guess what? By really narrowing it down, it means you are basically only correct for those few samples that ultimately ended up like directly on top of the true value. So in this case, like the 30% to the 28%, and basically anything else beyond that, too far away. The margin of error I'm building in just isn't quite enough to ultimately succeed in producing a correct estimate. Okay, so I'm going to bump it back up to our typical value before we go back. Okay. So once again, this is just an elaborate way of demonstrating this particular definition for confidence level. So a confidence level refers to the percentage of all possible samples that can be expected to include the true population parameter. So when we have a 95% confident, well, guess what? We expect that 95% of the samples that I get are ultimately going to create correct confidence intervals. And only 5% are going to be wrong. And, you know, once again, we saw this right here. It's only these 5% most extreme ones on the outside that were incorrect, and 95% of the nice ones on the inside that were close enough, well, basically within about 12 percentage points, were ultimately correct. Okay? All right. So that's confidence level. So I spent about 30 minutes or so talking about that. Okay. So what is making this margin of error bigger in the case of a 95 than in the case of a 90% confidence level? If we go back to the formula that we had, it was all connected to that critical value. Okay? And if you remember, that critical value changed depending on the confidence level, and really nothing else here had anything to do with the confidence level. So the key of getting this 95% of these samples to ultimately be correct must have something to do with that critical value. So that's what I'm going to present in this next page. Okay? All right, cool. So let me go ahead and resize this so you guys are kind of used to this. Okay, So the big question is, how is the critical value computed? Okay. Now, what I want to remind you guys is in essence, I want to remind you guys what kind of we just said about these estimates. And so remember that when we say we're 95% confident, what we're saying is that, kind of in some sense, we're saying that 95% of these samples are close enough to the real value that the margin of error that we're computing, that they're going to be closer than that margin of error, basically. 95% of them. Okay? And only the most extreme, only the 5% of most extreme possible values are going to be so far away that even when I try to make this compensation, that they're still too far away. They're so much farther than the margin of error that we're computing for them. Okay? And here's how that gets figured into our critical value. Okay? So what we are doing with our critical value, okay, so I want to remind ourselves that margin of error formula again, because it all kind of comes back to that. So we have this critical value, right? And then we're multiplying by this, okay? So p 1 minus p hat all over n. And if you remember this here is really just a standard deviation. Okay? This is really just a type of standard deviation when we talk about our when we look at all of our samples. Okay? What this z value is, or this critical number is, it really is a z-score. Okay? And that z-score basically is telling us, how many or what number of SDs do I have to go out to trap or to capture that percentage of the population. Okay? And so what we do to compute this value, remembering that our goal is to basically trap whatever percentage of the values. We want them to have that particular distance. And so what we do is we go to our standard z-score distribution. So this was the z-score distribution that we had back in chapter 6. Okay, so this was the one that was centered at 0 and just counted the number of SDs. So, like 1 and 2 and 3. Okay, and -1 and -2 and -3. Okay, and what the critical value does is we're trying to figure out how far do we have to go out, okay, and go below, okay, because remember we're both adding and subtracting that margin of error. So our critical value and the opposite of that critical value, okay, we're trying to figure out how far we have to go out, basically, to trap the confidence level inside this distribution. Okay? And what do I mean by the confidence level? I mean, 90% of the area, or 95% of the area, or 99% of the area. So we're just trying to figure out what this confidence level or confidence value, or critical value, we are trying to figure out how far we have to go to trap either 90%, 95%, or 99% in the center of that distribution. Or in other words, kind of looking back at our samples, we're trying to figure out how far we have to go out before we're going to start cutting off things that are too far to ultimately give me good estimates. Okay? All right. So I'm going to go down here. So this is our goal. Now what I'm going to do is I'm going to show you how it's done. Like, how are these numbers actually computed? And what we're going to do is we're going to use SALT, the built-in technology inside of your homework. Okay, and here's what we're going to do for SALT to get this particular value. So I have SALT already pulled out. Okay, we're going to use the normal distribution. Now I want you to notice here it has Z down here at the bottom, and this is counting the number of SDs. And if I set this at 0 and this at 1, then notice how the scale here matches the Z scale right underneath it. Okay, so right now we're just basically talking about our kind of Z-score distribution, or we would call it in technical terms the standard normal distribution. Okay, now how am I going to get the critical value? Well, basically what I'm going to do is I'm going to select between, since I'm talking about trapping things in the middle. We're trying to get those values that are close to the center. Okay, and then what I'm going to do is I'm going to change the probability, not these two values here, but what I'm going to change is this output value. And instead of 5%, I'm going to put in the confidence level. Okay, and I want you to recognize here, I put in the 95% confidence level right there. And I want you to notice here, it computed, when I put 95% here, it computed two numbers. What the two numbers that it just computed was that I have to go above the mean by 1.96 standard deviations and below the mean by 1.96 standard deviations so that I can get 95% of the area inside here. Okay, now this number should look really, really, really familiar. This 1.960, we usually call it 1.960. Well, 1.960 is the critical value that's associated with 95% confidence. 95% confidence. Okay? So I'm going to change it to some of our traditional values, like 90% confidence. Okay? So now I'm only trapping 90% of the area in the center there. I want you to recognize here, it has two numbers here. They're both exactly the same. One is positive, one is negative. The positive one is 1.6449. Now, does anybody remember what our critical number was for 90% confidence? It was 1.645. So this is where we got that 1.645. Now, just to show you guys that it works again when we use that 99%. Now look at that. What do we have? 2.576. 2.5758 technically, but 2.576 was the critical value that we used. So our steps for computing critical values, okay, is to go to our SALT distribution calculator, normal distribution, make sure we have a mean of 0 and a standard deviation of 1. We select between, and then what we do is we put the critical value right here. Oh, sorry, not the critical value. We put the confidence level right there. So if I wanted to find the confidence for, let's say, 80% confidence, the critical number for that. Well, the critical number for 80% confidence is going to be 1.2816. And we're always taking the positive one. Technically we have the negative one, but the reason that there's the negative one is because we're not only just adding 1.2816 times the standard error, we're subtracting that amount also. So we have a positive side to account for the upper limit and the negative to account for the lower limit. Okay, so you've watched our video for today. Okay, we have kind of two big ideas. Okay, we had what is the confidence level, okay, and we have how to compute a critical number. Okay, so what I'm going to ask you guys to do is basically answer two questions. Actually, let's make it 3 questions to make sure that you paid attention. The first question is, in your own words, what would it mean to have 82% confidence in a interval estimate? In a confidence interval estimate. Okay? So what do I mean when I say I have 82% confidence in the final estimate? 2, compute the critical value that corresponds compute the critical value that would be used for a 82% confidence interval estimate. Okay? And then number 3, what I want you to do is compute the critical value that would be used for a 100% confidence interval estimate. Okay? So we have basically 3 questions. In your own words, what would it mean to have 82% confidence in a confidence interval estimate? Compute the critical value that would be used for an 82% confidence interval estimate. Compute a critical value that would be used for a 100% confidence interval estimate. And actually, let's ask a 4th question. I'm sorry I always change this here. I had one plan in my mind, and then as I start to talk about it, I start thinking of other things I want to say. But what I want to say is that, is it possible to have a 100% confidence interval estimate? Okay, and for credit for this, I want you to explain your response. Okay, so I don't want you to say yeah, no, right? Tell me why, or what it would look like. What would it mean to have a 100% confidence interval estimate, and would it be useful? So I'd like you to actually write down and try to explain kind of your response to that. So these are kind of our 4 questions here, okay? I'm also going to put them in the assignment itself, okay? But I imagine that only people who watch the video will understand what these are, hopefully. All right? Well, I hope you guys have a nice weekend. I will see you on Monday, as long as I don't end up dying in the snow. Which I don't even think it's snowing, but I'm so scared of driving in the snow that I'm just sure that we're all going to die. On that high note, see you guys on Monday. Or if you see a sub, that means I'm dead. All right? See you on Monday.